all tech electives and all, and I have one grad for the only required class I'm teaching this semester is 407 heat transfer.
Heat transfer?
Yeah. Everything else is all electives.
Because that's third year. Is that in person?
It is, but I'm still doing Zoom.
You're
So
still doing Zoom.
basically exactly the same as I did last semester. So like,
Where is it? Where are you teaching?
it is E201.
E201?
Yeah.
Okay. You know what days?
Yes, today, Monday, Wednesday, 2:30 to 4. I can give you the Zoom link. That might be more.
Oh, I can do that. I'm wondering, like, I only asked because I'm putting together a little like 5-minute slideshow. And I was trying to do some recruiting for Rocket.
Yeah.
And I was wondering if I could like give like a 5-minute spiel to any juniors in your class.
Oh, for sure. Yeah, definitely.
But it might not be until like next week or something like that.
Okay. Yeah. Just email me and then we can set something up.
Awesome. I appreciate it.
Later.
Were you outside? Downstairs?
Yeah, so he told me when I called
Good,
him,
it's great.
Nice.
Yeah.
he was like,
I actually prefer
man,
to
this
talk
thing
in
looks
report.
like a- did you see what it's
So,
weight of aluminum? I was
It's
like,
kind of
well,
nice just
not
having an
comparing
option,
it to
even
the
though like
machine, comparing it to,
the
like,
recording
stock
for me
camera.
are like 3 gigs.
So
Yeah, that's true.
okay,
It kinda
maybe it'll
sucks,
be fine.
but
He turned it into
I don't wanna,
aluminum
like, not
model. It's like,
attend class.
it
but
should
it
still
kinda
be
sucks,
lighter,
you
it
know.
should be close. But then he's like said there was this,
I'm
like
gonna go into
he
this
had
one.
something he was looking at,
no, I'm
like
good. I
maybe
already
actual, like,
watched
sheets of paper for buying it. And he was like, oh, it says the density. So I'll ask him if we can get legit. Yeah, I'll ask him for legit info because I'll tell
I
him.
was
the info you
preaching
sent
him
me
about
was, like,
60
the
grabs from
same.
them. So I started reaching my arm around and I told you I've been working out. I sprayed the shit out of my tricep. Because apparently I don't stretch properly. I was like, oh my god.
You're supposed to stretch after working out. You should know.
I know I should, but I don't because I'm
Oh,
like,
by the way, so everyone in 417 today, we're going to be doing a Matlab activity, and so if you want to open up Matlab on your computers, to and then you can be ready to go. I'll make the announcement again once the lecture starts.
Basically, what Danny was trying to do for the loading.
Oh, yeah, he showed me that. Already was like a little model.
Yeah, basically, kind of like that.
At least the drive back home will be clear.
I hope so. Sometimes the 91 doesn't feel like
Ah.
so hopefully
Yeah.
You just see.
it'll be better than it was at 30 either way. So.
That's true.
I'm sorry, they were Dr. Banks says when I take the training or whatever.
Oh, yeah.
What do you do?
Probably.
Apple things always give me an issue. I can't connect my iPad to Zoom right now.
We were just talking about that.
Yeah. Either one.
Am I connected to the internet? I should be. Oh, I'm not. That's because this is the first time I'm bringing this here. That would do it.
Plans for the weekend?
Looking for houses again.
Oh, yeah.
Oh, fun.
How's that house hunting going?
Oh, it's awful. I was telling Suba earlier this semester.
I feel for him though, because I literally just, went through that.
Yeah.
It's like every single free moment we had with house hunting.
Yeah. same.
Yeah, that's the big thing is like it just takes up so much time.
Yeah.
Only to hear no every
Yeah.
time you finish it.
That,
So
yeah.
excited.
Every time it's like you're too poor, bro. You don't you
Yeah.
can't buy this house.
How much money do we need to make?
It's like more than enough.
Yeah.
I remember one of my buddies, they found a nice home in Santa Clarita. They got outbid by like 300.
Gee,
So,
300?
yeah.
Oh my goodness.
Yeah, they were like, man, why? Why?
Yeah.
Who the fuck wants to live in Santa Clarita? That badly, at least.
That's why people go to Riverside. I know people who live in Riverside. That's why you move because you hate your life.
Yeah.
As we're trying to like a house there. Hopefully you're not looking for a house in Riverside.
I am actually. So I'm looking in like Riverside, San Bernardino, everything.
They're selling houses in my neighborhood. I'll send you the link with the neighbors.
Okay.
Yeah, we can commute to school together. It'll be great.
Nice,
So there's
nice.
one spot.
You pay for the parking permit, okay? That would be funny though. She's like, hey neighbor. How's it going?
You'd actually try to avoid it.
think that's for the best. Like, no, I can't help with your homework. Saturday afternoon. No, what is it?
We actually have like a faculty neighborhood in Buena Park. And so like they're owned by Cal State Fullerton, but you kind of like buy the houses from them. But it's but I mean they reduce the cost, which is good. But then there's a market cap, and so you know it's not a very good investment. But if it's something that you just want to live in, then it's good for that.
That's kind of cool.
I'm thinking like blue. I started it literally I think it was like
We're gonna write code from scratch, or is there a file that we should download?
We are going to write it from scratch today.
All right.
We'll go through line by line. Don't worry. Yes. And so for those of you just joining us, this is for everyone in the classroom too. So today we're going to be doing we're going to write our first MATLAB code together. And so if you want to open up your computers and open up MATLAB, then we can be good to go. We'll probably do it probably like 20-30 minutes into the class, but yeah, just have it ready. Yeah, I thought we'd do the first one all together just so that we're all, you know, we're all on a good page. Okay, it's 5:30, so let's go ahead and get started today. Good evening, everyone. How's everyone doing today? Good. Our second day back in the classroom, although you know, we still have a lot of people on Zoom, so welcome to all the Zoom people. Okay. So today the plan is we're going to pick up basically right where we left off on Monday, talking about finite difference approximations or finite difference solutions to diffusion problems. And so hopefully today will be an exciting day because, you know, I think we've been doing we've been going pretty heavy on the theory for the last week and a half. And today you'll kind of see the payoff of everything. And so we're going to write our first MATLAB code together and we're going to see the finite difference solution to this problem. And you'll see that it's, I haven't been bullshitting you for the last week and a half. It actually is legit stuff, which I know, you know, it can be sometimes hard to see, you know, until we actually do the problem. So with that said, you know, if you're just joining us right now, we are planning to do some MATLAB today. And so if you're joining us on Zoom, if you can open up MATLAB and have it just running in the background and open up a new script, then you know, we'll be good to go. We probably aren't going to use MATLAB until maybe about 20 or 30 minutes in, but you know, just have it ready until you know, just so that we can go out there. And to that end, I did post your next homework assignment, and so homework 2 is up on Canvas. and there is a pretty significant coding portion on that. And so I think there are 3 problems overall, and each of them have multiple parts. And I think there's 3 codes I want you to write in the homework. But for the homework problems, I did give you a starter code for those ones. So those ones you don't have to write from scratch. But today, just so that just because this is our first time, I thought we'd write one from scratch. Okay. Okay, and so that's all my announcements. And so are there any questions I can answer before we get started? Okay, all right. So let's go ahead and resume where we picked off. Resume where we left off. Okay, so when we last left off on Monday, we were working on an example, right? And so our example was basically, this simple differential equation. Okay? And so it was d squared phi dx squared is equal to 6x, right? So that's the equation that we're interested in solving, right? Let me just double check that real quick. Yes, okay. And the boundary conditions that we have for this equation are phi at 0 is equal to 1. Okay, so we have a Dirichlet boundary condition there. And our other boundary condition was a Neumann type boundary condition, where we said d phi dx at x is equal to 1 is equal to 0. Okay. And our domain for this problem is 0 is less than or equal to x, which is less than or equal to 1. Okay. Okay. And so the first thing we did on Monday was we took this equation, because it's just a simple first order, a second order differential equation. We could just simply integrate this and solve for phi of x. Okay. And so we have the analytical solution for this, which is going to be nice because we're actually going to use that to check our solution. Okay. Okay. Right, and then the thing that we're going to check is actually our finite difference solution. Okay. And so if you recall, the way that we apply finite differences to this equation is we simply just take our derivative here and replace this with a finite difference approximation. Okay. Okay. And so, this part's important because, I know we're going to be doing everything, Monday and today with the same example, but you can apply the same technique to any other second order differential equation. Okay. And so especially for the homeworks, you're going to need to know how to do this stuff right. Okay. And so I think, and I say that because, one thing I've noticed from people in the past for this class is that there's not really any formulas that you can just plug straight in for this class. This class is a lot more about the algorithms and a lot more about the techniques. And so what I want you guys to focus on, and I write my examples, like this on purpose, is to kind of focus on the process in which we're going through to get to our equations, because there's not really something you can kind of just plug in at the end. And once you get started in the homework, you'll kind of see what I mean. Okay. And so to that end, we have our second order derivative here. And so our finite difference approximation for this is going to be phi I minus 1 minus 2 phi I plus phi I plus 1, all divided by delta x squared. Okay. And this is equal to 6xi. And so if we multiply both sides of the equation by delta x squared, okay, then what we get is phi I minus 1 minus 2 phi I plus phi I plus 1 is equal to 6xi delta x squared. Okay. Okay. Well, remember delta x here is the grid spacing on our mesh. Okay. Because in order to apply this equation, we need to take our domain and then discretize it into a discrete number of points. Okay. And so for 1D problems, our domain is just one dimensional, so we just have a line, right? And so on one side we have x is equal to 0, and on the other side we have x is equal to 1. Okay. And for this particular problem, I'm going to discretize this into five points. Okay. Just kind of keep things simple. All right. And so those are the 5 points in our grid. Okay. And the way that we obtain our equations, remember we since we have 5 different points right here, we want to solve for the solution to this equation at those 5 points. Okay. And since we need 5 solution values, that means we need 5 algebraic equations. Right. And the way that we get those equations is that we take our finite difference equation that we have up there that we just derived and apply it to each of the different nodes in our grid. Okay. And so a useful way to organize this is to use is to list out all the different I values in your grid. Okay. Okay. And so for a grid of 5 points like this, we have 5 I values. And so I'm just going to go ahead and plug in all the appropriate I's into that equation. Okay. Knowing that for the first and last value here, remember what we talked about last time, that if you apply our finite difference equation to the first and last nodes, then you're not going to get a valid equation because then you're going to have nodes that are outside the boundary. And so I'm only going to apply this finite difference equation to just the interior nodes. Okay. So starting at I is equal to 2 and going to I is equal to 4. Oh, we can go ahead and plug in for delta x squared actually. So I think last time we said that since the length of our domain is 1, right? And we split it up into 4 grid points, or 5 grid points, excuse me, then delta x here has to be 1/4 or 0.25. Okay. And so if we plug that in and we say that we have 6 divided by 4 squared, which is 16, we end up with 3/8 times xi. Okay. All right. And so we have 3 equations there. Okay. And so the next step is we're going to apply our boundary conditions for I is equal to 1, I is equal to 5. Okay. And if we go back to our problem statement, we can see that our first boundary condition states that phi of 0 is equal to 1. Okay. Okay. And so if we transform this into our grid points, we know that x is equal to 0 is at node 1, right? Because that's where the left side of the domain is. And so to encode this boundary condition into into an algebraic equation, we can simply just say phi1 is equal to 1. Okay. Okay. For the fifth boundary condition, we're going to use a finite difference, right? Because our other boundary condition was a Neumann boundary condition at x is equal to 1. Okay. And x is equal to 1, we know is node 5. right? Because node 5 is at the right side of our domain. Okay. And so if we use a finite difference approximation for this, which in particular we're going to use a backward difference. Okay. Okay. Because remember, when we apply our Neumann boundary conditions, we have to put them in terms of the nodes that we actually have in our grid. Okay. And so we have to use a backward difference, because if we go from node 5, the only neighbor that's available to us is node 4, right? And so we have to formulate a finite difference scheme that incorporates phi5 and phi4. Okay. All right, and so we can go ahead and get rid of the delta x, because we can multiply by both sides. Okay. And so our algebraic equation for this, and I'll put it in this form, is minus phi4 plus phi5 is equal to 0. And so after applying our finite difference scheme to all of the interior nodes, and after applying our boundary conditions on our boundary nodes, we're able to get our 5 equations for our 5 unknowns. Okay. All right. So this was a recap of last time, and so this is kind of where we left off. And so are there any questions on anything we've done so far? Okay. All right, and so the next step in this problem is to turn this into a matrix. Right, because what we have is 5 equations and 5 unknowns, right? So we have a system, an algebraic system of equations, and so the the natural thing to do for this is to turn it into a matrix, and that's going to be really useful for us, because that's the form, or that's the most useful form that Matlab can solve these equations for us, is if they're in matrix form. Okay. All right, and so the matrix form of these equations will look something like this. Okay. Right, and so I'm using the form of the equations. Oh, question. Sorry, the audio here was off, so if I missed it, I'm sorry. All right. All right, question. So why did we set up the second step of this solution like this? I'm referring to 6x turns 6xi. Yeah, that's a good question. And so in the original equation, we had 6x on the right-hand side, right? And so the x here refers to basically the physical coordinate of the of those points. And so the reason I changed it to 6xi is because we're basically now evaluating this equation at the discrete points in our mesh. And actually, yeah, and I forgot to do that here. And so when we evaluate these equations at the specific I values, we're going to plug in the specific values for the xi's in those cases. Okay. And so just to kind of show it to you, so we have basically a 5-point grid right here, where we know the x value at node 1 is 0, the x value for node 5 is 1, and so we kind of follow that guidance. So we can say that x2 is equal to 0.25, x3 is equal to 0.5, and x4 is equal to 0.75. Right, and so we basically plug those directly into the equations, based on that coordinate. Question. So for the boundary conditions, will be given most of the time. The boundary conditions will be given to you all the time. And so this class, we mostly focus on solving complete problems. And so we're going to assume that all the problems that I give you will be fully defined. And so you'll have the boundary conditions all the time. Yeah. Yeah. Thanks for the point on xi. I did miss that from before. Okay. Oh, okay. And so next we want to put this into a matrix form, okay? And actually, let me go ahead and erase this, because it's going to, we're going to need a little bit more space. Okay. All right. And so the matrix form of these equations, I'm basically using the form AX is equal to B, okay? Where the A here is the coefficient matrix, right? And so for the coefficient matrix, I'm just going to take off the coefficients for each of the terms in this, for these equations. And we'll do them kind of one term at a time. All right, so one thing I like to do, you know, especially when you're writing these out by hand, is to not only label the rows, but also label the columns, because, you know, I think it makes it a little bit easier to do. Okay. All right, so let's start with the first row. So our first row is a simple equation. We have x1 is equal to 1, okay? And so the only coefficient that we have from that equation is we have a 1 that's going to be in front of phi1, okay? And then we have zeros for all the other coefficients, right? Because phi2, phi3, phi4, and phi5, none of them appear in that first equation, okay? So we're going to have all zeros there. And then on the right side of the equation, which is, you know, these guys right here, I'm going to go ahead and put in that value. And so in this case, the right-hand side value is just 1, because that's what the Dirichlet boundary condition is. Okay. Okay. And so that's the Dirichlet boundary condition. And so you can see we have a row, very simple row. So it's just 1, 1, 0, 0, 0, 0. Okay. Our next row is 1 times phi1 minus 2 times phi2 plus 1 times phi3, right? So let's go ahead and pop in the coefficients for that. And so we have a 1 in front of phi1. We have a minus 2 in front of phi2. We have a 1 in front of phi3. And we have zeros for the other slots, okay? For the next equation, we have a 1 in front of phi2. We have a minus 2 in front of phi3. A 1 in front of phi4, and zeros for everything else. Okay. And then the exact same thing for the next row. And so for the next row, we have 0, 0, 1, minus 2, 1. Okay. And then for the last row in the equation, we can see here we have a minus 1 in front of phi4 and a 1 in front of phi5. Okay. And the right-hand side is 0. All right, and so all that's left here is to basically fill in the rest. And so I'm just going to leave these in equation form. And so we have 3/8 times x2. Okay, we have 3/8 times x3, and then 3/8 times x4. I guess these aren't. I could have plugged these in, because remember x2 is 0.25, x3 is 0.5. And x4 is 0.75. So I guess I could have plugged it in, but I was lazy. Okay. Okay. And that's it. And so that's our matrix set of equations. And so hopefully it looks familiar. And so if you remember, one of the programming questions I asked you on the first homework asked you to build a matrix that looks very, very similar to this. Okay. And so that was basically preparation for, you know, what we're going to do today. And so, you know, the matrix structure of, you know, -2 and then 1s on the off diagonals is, you know, that's basically a diffusion problem. Okay. And so the next step here, you know, of course, is to solve these equations, because remember, what we want is the solutions for phi1, phi2, phi3, phi4, and phi5. Okay. But the nice thing here is that, you know, this is where MATLAB is going to take over, because, you know, you don't have to solve the system of equations by hand. Okay. And I'll show you how to do that in MATLAB. I know we talked about it briefly in our MATLAB crash course, but, you know, I think once you actually try it, then you'll see. Okay. All right. Any questions on this before we start doing MATLAB coding?
Is x5 set to be 0?
X5. So we don't have X5 there. So the right-hand side of that equation came from the boundary condition, the Neumann boundary condition.
Okay.
Yeah. And so we only need x2, x3, x4, you know, because those are the interior node equations.
Okay, I see what you mean.
Yeah. Mm-hmm. Right. Okay. So if everyone can open up MATLAB, and then we can go ahead and get this show on the road. Okay. And so actually, I'm gonna kind of switch back and forth, because I think that's kind of the more useful thing. But I don't have MATLAB on this iPad, and this mouse is jank as hell, and so I can't draw on here. So I'm going to kind of swap back and forth between iPad and computer. Okay, so let me go ahead and share. All right, so I'm gonna go ahead and open up MATLAB, and the keyboard is over here, of course. I told everyone to open up MATLAB, but I didn't do it myself, so I'm a hypocrite.
Good question.
Yeah.
For the fees 1 through 5, since we're solving for that, and we're taking the range from 0 to 1,
Mhm.
those values should sit in between 0 and 1.
Yeah. Mhm.
Okay.
Yeah. So we're for the most part in this class, we're going to assume that the grid points are evenly distributed, and so we're not going to work with any non-uniform grids. Although in theory, you could apply the same methodology to that. It's just you have to be more careful with the grid spacing. But just to keep things simple in this class, we'll mostly assume the grid spacing is uniform. Yeah. Yep. Okay, so here we have MATLAB, and so I'm going to do this in kind of a split screen. This is how I usually like to use MATLAB, and so I'd like to have the console on one side, and then we're going to open up in a script on another one. Okay. Okay. And so one thing that and you don't have to do this, but this is just how I learned it, and it's just I just always have to start this. So I always start every MATLAB script with clear all, close all, and CLC. Just so every time I run the script, I know it's a fresh thing. Can everyone see that? Okay. Let me open up. Or let me increase the font size here because I think it's a little bit hard to see. Editor fonts.
It looks good on Zoom.
It can look better though. There we go. Okay, 14. I think that was a sweet spot from before. Okay, and so one way that you can solve this equation, solve this system, now that we've kind of gone through all the work of deriving that matrix, is we can just solve this kind of directly. And so one thing that you can do is that we have our 5 by 5 matrix, and so you can just go ahead and input the entries one by one. Okay. And so our first row is 1, 0, 0, 0, 0, and then we have 1, comma, minus 2, comma, 1, comma, 0, comma, 0. Okay. Then we have 0, comma, 1, comma, minus 2, comma, 1, comma, 0, dot, dot, dot. We have 0, comma, 0, comma, 1, comma, minus 2, comma, 1. Okay. Last row is 0, comma, 0, comma, 0, comma, minus 1, comma, B, right-hand side is 0, semicolon, 3/8 multiplied by 0.25. Then we have 3/8 multiplied by 0.5, 3/8 multiplied by 0.75. And then we have 0. Oh, excuse me, the first entry here is 1. Okay. Right. Okay. And so if we go ahead and run this code, you can see here that it's created 2 matrices for us. Okay, so we have one matrix, or excuse me, we have one left-hand side matrix, and so this should have the same coefficients that we just derived in our notes. Okay, and then the B vector has the values of the right-hand side there. Okay. Right, and so we have our left-hand side matrix and our right-hand side vector solved. And so to compute the solutions for phi, okay, we can use what's called I call it the backslash notation. Okay, I'll call this phi direct. Okay. And so phi direct is going to be A, which is your left-hand side matrix, and then you're going to use a backslash. And so if you're unsure where the backslash is, it's the key right above the enter key. Okay. Right. So A backslash B. Okay. And we hit run. And there is our solution. Okay. That's it. Let me go ahead and comment these out a little bit more. So this compute left-hand side matrix. This is compute right-hand side vector. Okay. Right. And so if we know the matrix beforehand, and we know and we know exactly what all the equations are, you can just input it directly into MATLAB. Okay, and here's our solution. Right, so this is probably the most direct way that you can solve for a linear system of equations, but it's also the least useful for this class, because a lot of times, you're not going to know exactly what the equations are, and in this case, we only did a grid of 5 points, and so 5 is, not that much in the grand scheme of things. And so a smarter way to build this code up. Okay, a smarter way to build this code up is to build it directly off of the finite difference equations. Okay. Okay. And I'm going to show you hopefully two ways today. And so I'm going to do one way which kind of is fixed for this, and then I'll do another way which is actually the start of your homework, which uses a loop to go through the whole thing. Okay. Okay. But any questions on this so far? So this is kind of just really straightforward. Just, I have this linear system. I know what the coefficients are. And so let me go ahead and solve for the solution. So everyone okay with this?
Sorry, I can't really see your solution. Which one is the same?
Oh, yeah. So the numbers for the solution are phi1 is equal to 1. Okay. P2 is equal to 0.4375. Okay. P3 is equal to minus 0.0312. Okay. P4 is equal to minus 0.3125. Okay. And P5 is also the same thing. Yep. Okay. All right, so let's do a smarter way to kind of implement this code, because this is kind of like a it works, but it also doesn't really teach you anything, and it has really nothing to do with finite differences at all. Okay, and so let's do a different way. Okay, and so the first thing we're going to do is we need to define the locations of all the grid points. Okay. And so remember in our example, I had a grid points of 5, right? And we said that x1 is equal to 0, x5 is equal to 1, and then everything else was evenly spaced up to that point. Okay. And so we can do this with a single function in MATLAB. Okay. And so we went over this briefly in our MATLAB crash course. Okay. And so the function we're going to use for this is Linspace. Okay. And so let me go ahead and define a variable here. So I'll call it pos vector. And so pos vector stands for position vector. Okay. Okay. Right. And so I'm going to call a function here called Linspace. And so by calling this function Linspace, what we're telling MATLAB is say, give me a vector where the first entry in the vector is 0, the last entry in the vector is 1, and the number of points in the or the number of entries in the vector is going to be 5. Okay. So let me go ahead and run this. Okay. And so after you run it, you can go ahead and look at the results. Okay. And if you can't see this, basically it's 0, 0.25, 0.5, 0.75, and 1. Okay. And so if we want to basically reference, or basically we want to find out what the x coordinate of a certain grid point is, we can just read it straight off this vector. Okay. And so as an example, if we wanted to get the position of grid point, let's say 3, we would use this vector here. So we use pos vector, and we would reference the third entry of the vector. Okay. Okay. Right. So does that make sense about why we did this? Okay. So I'm doing it this way, or I'm showing you this because later on in the homework, I'm basically going to have you extend this code have many more grid points. So instead of 5, it would be 50. Okay. And so for 50 grid points, I'm just going to run this really quick. Okay. You can see here for 50 grid points, it's really useful because the grid spacing is not that uniform. Okay. But we'll keep it just to 5 now. Okay. And so this Linspace vector is really useful because it lets you kind of compute what those grid points are really easily. Okay. Okay. And so the next thing that we need in the code is we need to have our grid spacing. Okay. All right. And so our grid spacing here is actually, pretty straightforward. Okay. And so our grid spacing here is going to be, or one way we can compute it is we can just take our pos vector and take the difference in between any two entries. Okay. And so we'll call the grid spacing dx. And so that's in reference to delta x in our solution. Okay. And so you can see here that I'm taking the difference between the second entry in the position vector and the first entry in the position vector. Okay. And so what that'll do is that, as you can see here, that the second entry in the position vector is 0.25, and I'm subtracting the first entry, which is 0. Okay. So I'm doing 0.25 minus 0. And so this gives us our grid spacing. Okay. And so that's going to be important to us, when we actually go and solve the equation. Okay. Because this is something we're going to need to plug in, plug into our equations. Okay. Any questions on that? Does that make sense how we got the grid spacing? Okay. Okay. Now we need to actually start, populating our equations. Okay. Okay. And so the best general way to do this is to first create empty matrices, an empty matrix and an empty vector. Okay. And the main goal for this is to for them to hold the coefficients or our finite difference equations. Okay. All right. And so, since we know we're going to have 5 equations with 5 unknowns, we're going to create a zeros matrix with 5, 5. Okay. And so that's going to be the left-hand side matrix. Okay. And remember, the left-hand side matrix, this is where we're going to put all the coefficients of phi. Okay. Okay. And the right-hand side vector is going to contain all the boundary conditions and any kind of production term or generation term will go here as well. Okay. All right. And so for this particular problem, our production term, was 6x, right? And so the contribution from 6x is going to go into the right-hand side vector. Okay. Okay. And so we can go ahead and run the code right now. We can kind of see where we are. Okay. And so if we run the code, you can see here that we have a variable called dx, and so that has the grid spacing of 0.25, and so that's good. Okay. Let's check the left-hand side matrix, and so the left-hand side matrix is all zeros. Okay. And so that's good. And so it's a 5 by 5 matrix with zeros all the way around. Okay. Okay. And the right-hand side vector, is all zeros as well. Okay. And so the next step in this problem is to actually, is to actually input the coefficients at the matrix and the vector. Okay. And let's do this one equation at a time. Okay. And so let's start with the first equation. Okay. And if you recall from our hand calculations, our first equation was simply our Dirichlet boundary condition. Where our Dirichlet boundary condition was phi1 is equal to 1. Okay. All right. And so if you look back into your notes, the notes basically have our first row in the matrix being 1 in the diagonal entry, and then zeros all the way across. Okay. And so the way that we're going to input this is we're going to have a left-hand side matrix. Okay. We need to reference the first row and the first column. And so that's going to be left-hand side matrix at 1, 1. That's going to be equal to 1. Okay. Then we're going to set all the other entries. Okay. Okay. And so all of these 5 things together, this is our first row in the matrix. Okay. And that first row, remember, corresponds to that first equation. Okay. Notice how, when I'm referencing these entries in the matrix, all these are ones. Okay. And so that all refers to the first row in the matrix, because remember we reference matrices by row and then column. Okay. And then all the columns are just are just 1, 2, 3, 4, 5. Okay. But wait a minute. This is we've kind of done a lot of extra work here, because if we look at our left-hand side matrix, remember we started with a zeros matrix, right? And so everything by default in this matrix is already 0. And so all of these lines of code right here that we're setting to 0, we don't actually need this because they're already 0. And so there's no point in kind of assigning it to be 0 again. And so all of this is unnecessary. And so you can just delete it, but I'm just for now I'm just going to comment it out just to show you that it's not necessary. Okay. Okay. All right, and so the next thing we need to do for the first equation is we need to set the right-hand side. Okay. And so the right-hand side vector in this case, which is our Dirichlet boundary condition, is just 1. Okay. And so if you look back in your notes, you can see that was our first equation there. And so if you want to write this kind of really compactly, you can just go ahead and kind of get rid of all of these lines right here, because we don't need to set the lines equal to 0 anymore. Okay. And we just end up with these 2 lines of code right here. Okay. The left-hand side matrix and the diagonal entry is 1, and then the right-hand side vector in that spot is also 1. Okay. Any questions on this so far? Okay, so let's go ahead and run this just so you can see. It's not going to be the most exciting thing, but keep your eyes on this entry right here. Okay. And so we ran it, and it turns into 1. Yippee-ki-yay. Okay. All right, so that's the first equation. So now we're going to do the second equation. Okay. And if you recall from our example, this was an interior node with the finite difference equation applied to it. Okay. So this will be kind of an exciting row, because we have we have 3 entries in our left-hand side matrix. Okay, so let's start from the left to right. And so if we look at the second row of the matrix we derived in class, you can see that the first entry is 1. Okay, it should be left-hand side matrix. A little bit ahead of myself. Okay, and the diagonal entry at 2, 2 is going to be -2. Okay, and then the entry at 2, 3 is going to be 1. Okay. Okay. All right, so that's all of the left-hand side matrix entries. Now let's do the right-hand side vector. Okay. And since we're doing the second equation, this is going to be the second row. Okay. And I'm going to do this actually straight from the equation. Okay. And so if you remember, our original equation here was, I'll write it kind of really poorly here. Okay, so we had d squared phi dx squared is equal to 6x, right? And so after we did our finite differences, we end up with, on the right-hand side, I'm not going to write the one on the left, we end up with 6xi times dx or delta x squared, right? And so I know in the class we actually evaluated what that 6xi delta x squared is. But with MATLAB, MATLAB can do a lot of that arithmetic for you. So let's go ahead and let MATLAB kind of compute this for us, just to kind of prove to you that we are kind of solving the same problem. Okay, and so basically the equation that we're going to input here is 6 times xi. And remember, the way that we obtain xi is we reference our position vector, the one that we defined earlier. Okay. And since this is the second row, we're going to do pos vector at 2, and then we're going to multiply by the grid spacing squared. So we're going to multiply by dx squared. Okay. So that makes sense. That makes sense to everybody. Okay. All right, so we can go ahead and run this, and we can go ahead and check our matrices again. So you can see in the left-hand side matrix, we have 1, -2, 1. And then in the right-hand side vector, you can see here that our first entry is 0.0938. Okay. And if we compare that with the B vector that we had earlier, the one where we input things manually, you can see that we have the right value there. Okay. And so that's good to know. Okay. All right, so the third and fourth equations are more or less the same thing. And so I'm going to go ahead and type it, and I'll let you guys kind of do it yourself. Okay? And so we're going to have assign three coefficients just like before, but just be careful because they're shifted over 1. And so, you're going to start, instead of starting at 2, 1, you're going to start at 3, 2, right? Because the first entry of the third row, the first column of the third row is 0. And so, you start from here. Okay. All right, so go ahead and fill in the rest for the third row and the fourth row, and I'll meet you back here in about 5 minutes. You guys might be faster than me because I'm gonna type comments here. How's everyone doing? I heard a silence of no clickety clacks anymore, so I'm assuming everyone's caught up. Okay, and so if you wrote those three equations, okay. Oh yes, I can. Let me show you lines 20 to 40. Yeah, I'm gonna go ahead and talk a little bit. Yeah, and so if you input those equations 2, 3, and 4, your left-hand side matrix should look something like this. Okay, and so it should look like the first four matrices in our notes, and your right-hand side vector should look like this. Okay. Any questions on this so far? Okay. All right. And so the last thing we need to do is just the Neumann boundary condition, and so that's the last entry. Okay. And so let's go ahead and input the fifth equation. So this was our Neumann boundary condition. And here we only have two entries, since we have left-hand side matrix at 5, 4 is equal to -1. Okay. We have left-hand side matrix at 5, 5 is equal to 1. Okay. And then on the right-hand side vector, we just have 0. And so I guess we don't need this, but I'll just go ahead and put it anyway. All right, so we just go ahead and run it one more time. All right, and you can see here that we have this. Okay, and so we're all good to go. All right, and so the last step here is just we're going to solve this. We're going to solve this equation. Okay. Okay, and so just like we did up there, I'm going to use the backslash notation. And so we have phi. We'll call this phi solution. Okay, there's going to be left-hand side matrix backslash right-hand side vector. Okay, and we see if we go ahead and run that, we get our phi solution should look exactly the same as our phi direct. Okay. Okay. And that's it. Right, and so we've successfully implemented our first code. It's not the most efficient thing, but I wanted to do it this way because I think this is a good setup for how you're going to do things on the homework. And let me do this. Let's plot this. Let's look and see what this looks like. It's one thing to look at kind of a vector of values like this, but I think it's a lot nicer to plot this. Okay, and so to plot our solution, I'm just going to make a figure, and I'm going to plot. And so we need an x value. So this is another benefit of using the pos vector, is that it gives us an x vector to use for plotting. Okay. And so pos vector is going to be our x values, our phi solution is going to be our y values. Okay. And you don't have to do this, but I'm just going to do it just to make it easier to see. Okay, so I'm going to change the line width to 2. Okay. And if we run it, then it looks like this. Okay. Right. Let's compare this to our analytical solution, right? Because we actually did find the analytical solution to this problem. Okay. Okay. And this is the part where I show you that I haven't been bullshitting you this whole 2 weeks. Okay. And so for analytical solution, let's do this. So X analytical, we definitely can't hyphenate that. That would be awful. Okay, so X analytical. I'm going to do Linspace. And I'm going to plot the analytical solution with 100 points just to make sure that it's a smooth curve. Okay. Okay, so we have phi analytical. And if you remember from last time, our analytical solution was x cubed. Okay. And so this equation was simply just x cubed minus 3 times x plus 1. Okay. So that was the analytical solution that we found last time. Okay. All right, so I'm gonna go ahead and plot this on the same plot as our solution up there. Okay. Let's go ahead and do that. All right. And let me put a legend of this too, actually. You don't have to type this stuff, but this is just for me showing you guys. I am going a little bit fast right now. Okay. And so you can see here, this is our comparison. Okay. And so in the blue right there, we have the finite difference solution. And so that's what we obtained by from our equations. And in the red, we have our analytical solution. Right? And so you can see, this, okay, this is not the best matching, I have to admit, but you can see that they're following a similar trend, right? So they all start from the same point, okay? And then as you get further away from there, it tries to do this kind of, this curvy thing right here, okay? All right, and so that's our first code. And so, are there any questions on any of this?
Yeah, quick question.
Yeah.
To get it more like an analytical solution, would we just add more data?
Exactly. Yes. Yeah. So that was the next point I was going to make. So if you do want them to match better, then you would just add more grid points to that. And that's what your homework problem is to basically extend this script to I think it was 40 points. And so with 40 points, you should see them match up, almost exactly. Yeah. Yeah. All right, so that is the next thing I want to cover. I'm not going to write the whole thing for you, but I do want to give you some hints just to get you started. Okay. So there's a couple more things I want to go over today. Okay. All right. And so let me go ahead and come down here a little bit. Okay. And so for the homework, you need to extend this script for. I think it's 40 points. Okay. Bless you. All right. And so you're going to need to extend the script for 40 grid points. And so, there's a couple ways that you can do this. You could kind of do it the same way that we did here. Bless you. Where we have where you basically just manually type in each equation. So you go first equation, second equation, third equation, fourth equation, fifth equation, sixth equation, yada yada yada. Okay. That's one way you could do it. It's not a very smart way to do it, but you can do it. And so another way that you can do this is you can, instead of assigning each matrix row individually, is to use a loop to assign this. Okay. All right. And so let me start you off here. And so let's say that let's say that we want to do 40 points. Okay. The nice thing about this way is that you can you can make it flexible, and so you can make it adaptable to how many grid points that you want. And so as long as you store the grid point as a variable, you can vary that as much or as little as you want. Okay. And so just like before, I'm going to make a pos vector. Okay. And I'm going to use Linspace for that. And so if you recall the way we used pos vector before, we input input 5 grid points. Okay? But in this case, I'm inputting n, which indicates that we want 40 grid points. Okay. Okay. And so just like before, we're gonna have a left-hand side matrix. Okay, it's going to be n by n. And so our left-hand side matrix here is now 40 by 40, and our right-hand side vector is also 40 by 40. Okay. Okay. And so this thing wasn't in the way. Okay. And so if you look at the left-hand side matrix and right-hand side vector, you can see now that they're 40 points. They're 40 points each. Okay. And so now at this point, we're basically at the same point that we were, here. Oh, we need the grid spacing. Grid spacing dx is equal to, what is it? Pos vector at 2 minus pos vector at 1. Okay. So we need the grid spacing just like we did before. Right. Now we're at the point where we need to assign values / coefficients for the left-hand side matrix and right-hand side vector. Okay. Again, the best way to do this is with a loop. Okay. Right, and so with this loop, you're going to visit every row in the matrix, and so we're going to loop it from I is equal to 1 to n. Okay. And then from there, you're going to build up the matrix. Okay. All right, I don't want to spoil too much because I did give you a starter code for this one as well. So you can definitely look at the starter code. I think it should have all these similar elements. Okay. And if you fill in the starter code, then you're going to be able to get a finite difference solution that looks much better than this. Okay. And for this one in particular too, definitely check out the coding practice that I gave you for the first homework. And hopefully this is ringing some bells. This oh, I just deleted it. Okay. And so hopefully this structure here is ringing some bells from when you did your homework, right? And that was kind of very intentional. And so look at the logic that you use to create this matrix for the homework. The one here is a little bit different. I will admit it's not exactly the same as the homework or as the last one, but a lot of the same principles and a lot of the same techniques you can still apply here. Okay. All right. And so actually, let me go ahead and double check what that starter code looks like because we are running a little bit ahead. Or 17. Go to assignments. Homework 2. Okay. And so you can see here, I provided you starter codes for each of the different problems. Okay. And so the problem that that I'm talking about here is problem 2A. Okay. And so you can see here, it has a lot of the same values here as well. Okay. And so I've already written the loop for you. And so the only thing you have to do here is input everything that says to do. Okay. And so for a lot of the homework assignments, I'm going to give you starter code that looks like this, where anytime I want you to write code, I'm going to mark it with a comment that says to do. Okay. And so whenever you see to do in the code, then that's something that I want you to write in yourself. Okay. But you can see here that it starts very similarly to what we've kind of started here already. Okay. And so kind of combine the logic that we use to make these equations, and then combine it with the what you know about for loops and if statements, and you should be able to to knock this out pretty easily. All right. Any questions on this?
Question, just for the home, you didn't want the scripts at
Yes. Yeah. So if you can put it, it doesn't have to be one PDF, but if you can convert your codes to PDFs, then that would help me out a lot. So if you're in Matlab and you are on the screen right here and you wrote it as a separate script, what you can do is you can do save as, and you can use, oh, sorry, I think it's export. Let's see. Share screen. Let's see. If you go to print, yeah, if you go to print, come on. Basically, if you do print and then there's an option to print it to PDF, then that's usually the best way.
Publish.
Or publish to, yes. I would, but it's frozen. Okay. All right. I'll let it do its thing. And then anyway, that's the conclusion of our Matlab portion of the class today. Go ahead and cancel this. Yeah. So if you print, you can do Adobe PDF and you can print it that way. Okay, all right, so let me go ahead and bring it back here. Right, and so there's one more concept I want to talk about today, before we wrap it up for the week. Okay, and it again has to do with errors. Okay. We're going to be talking about errors a lot in this class, and it's, I know probably you're going to be sick of it by the end, but it's an important thing to know, for for this class, because it's basically how you assess how good your code is. Okay. Okay. And I want to bring this up again, because we have this really nice, really nice feature in 1D problems, and that we often know what the exact solution looks like, or what the analytical solution looks like. Okay. Okay. And so we can compute the error very simply as just the difference between your computed solution and the analytical solution. Okay. Okay. And of course, just to make sure that it's positive, you can take an absolute value. Okay. All right. And so in the code that we just wrote, we had that solution, phi analytical. Okay. And so what you can do is you can just simply do phi finite difference. Okay. So I'll call it phi FD minus phi analytical. Okay. And this is going to be your error. Okay. So I'll call it E for now. And so if you have the analytical solution, it's very easy to compute in MATLAB. You just simply take the difference between those two vectors. Okay.
That is a phi underscore FD, correct?
Yes. Yeah. Okay. And so it's just a simple difference between vectors. Okay. Okay. All right, and so what happens if you let's see what happens when we actually did this for our previous example. Okay. Okay. And actually, let me go ahead and draw the two for you, just so that you can kind of see. Okay. And so if you recall, our analytical solution looks something like this. Okay. And then our finite difference solution looks something like this. Okay. Not exactly, but actually, let me fix this a little bit. Something kind of like that. Okay. All right. And so, I want to kind of draw your attention to some of the trends, right? And so what do we see here, right? Right. In particular, I want you to, to look at this graph and see, where is the error the smallest? Okay. The error is smallest, of course, over here. Okay. Next, let's observe where the error is the largest. Okay. The error is largest on the right side of the graph, or I should say right side of domain. Okay. Okay. That's no accident. Okay. Let's think about what else is happening on those sides of the domain. Okay. In particular, I want you to think about what are the types of boundary conditions, or what are the boundary condition types that we applied there. Okay. And so what boundary condition did we have on the left? We had a Dirichlet boundary condition, right? Okay. Whereas on the right, what we had was a Neumann boundary condition. Okay. Right. So what does this tell us? And so this tells us that in general, whenever you have a Dirichlet boundary condition, you can expect the errors to be actually they're going to be basically zero at those areas. Okay. Meanwhile, errors are greatest near the Neumann boundary conditions. Okay. So why is this? And so why do we have much less errors in the Dirichlet boundary condition? Well, let's think about the definition of Dirichlet, right? And so the definition of a Dirichlet boundary condition is that, remember, we're directly specifying the solution values at those locations. And this is true for the finite difference equation and for the analytical solution, right? And so if we're directly specifying the solution to be what it is at those locations, it makes sense that they're going to be exactly the same. Okay. And so if we tell the solution it has to be this, for the finite difference and for the analytical, they have to be the same. Okay. The Neumann boundary condition, on the other hand, is a lot less strict of a condition. And so the Neumann boundary condition is a specification of the solution derivative. Okay. And so a Neumann boundary condition will make sure the derivatives are the same, but the solution value itself, there's no constraint or no restriction on that. Okay. And so if you look at the graphs that I drew here, you know, I didn't draw it very well, right? But what you can see here for these from these two curves is that they both should have the same slope. Okay, if I drew it better, you could probably see it. Okay, right. And so the Neumann boundary condition is going to make sure that they have the same slopes over there, but it doesn't make any specification of what the solution value itself is. Okay, and the way that we define error, you know, we don't define error in terms of the derivatives. We define error in terms of the solution value itself. Okay, and so if we're not going to place any constraints on the solution values, then it makes sense that there's going to be some room for error in those cases. Okay.
Do they ever converge?
They do, yes. And so if you refine the grid a lot, and you'll see this in the homework when you use 40 points, you're going to see those two graphs basically lie directly on top of each other.
Okay.
Yeah. All right. Any questions on this? Okay. Okay. And so the last thing I want to mention is different ways to quantify the error. And so, you know, we have this equation, but, you know, a lot of times we just want a single number to tell us, you know, how far off we are. Okay. Okay. And so there's a couple of things that we can do. Okay. And so one thing that we can compute is something called the total error. Okay. Right, because remember, using this equation that we have up here for error, you know, we're going to get a vector of errors, right? And so for basically every grid point that we have, you know, it's going to tell us what that error is. If we want to just have one number that sums up all the errors in our entire solution, we can just simply add them all up, right? And so if we just take the summation of 1 to n of all of the errors, okay, that would be like total error. Okay, and so you basically just sum them all up. Okay. And you can do this in Matlab very easily. I think the function for it is sum. Okay. Okay. Or another useful indication is average error, and so that'll tell you about averagely, you know, how far off you are, you know, from the analytical solution on a point-by-point basis. Okay. And so to get average error, you simply just take you take the total error and you divide it by n, the number of grid points. Okay. Okay. Usually for me, I you know, just because it's a lot easier to interpret, I like to use average error because that'll tell you, you know, how far off you are just on average. And so you can interpret it very physically, very intuitively. Because if you look at total error, you know, that's going to depend on how many grid points that you have. And so if you have like 1,000 grid points, you know, your solution might actually be very close to the exact one, but because there are 1,000 grid points, you're adding up 1,000 different little errors. And so it might make it seem like it's much bigger than it actually is. But if you take the average error and you divide by the number of grid points, I think that gives you a much better sense of how good your solution is. Okay. And one thing that you can do for your homework, I don't ask you this specifically, but you can test and see how good your finite difference solution is depending on the number of grid points, right? And because remember, you know, the scheme that we're using for this diffusion equation is a second order scheme, right? And so that tells you that if you double the number of grid points, or in other words, if you decrease the grid spacing by a factor of 2, then you should get 4 times as much accuracy. And so it'd be interesting to kind of test that out and see if you actually get that, observe that in your solution. All right, any final questions on this before we wrap it up for the week?
Yeah, I guess you kind of answered, but I just kind of want to like, so the errors is just more of like when, because if you're saying that if we just need to increase our grid spacing, then we can overall get closer to our analytical solution.
Yep.
So then what's the point of the errors, and if we can always almost converge, kind of like directly see.
Yeah. No, it's a good question. And so, you know, the question is, you know, what's the point of the error if we can always kind of converge to the main one? In these 1D problems, you know, you should always be able to converge on the main solution. But once you get into 2D and especially into 3D, increasing the grid size is a much more difficult task because you're talking about like a three-dimensional mesh. And so the cost for those types of simulations jumps up pretty dramatically.
Oh, I see.
Yeah. And so it's actually a trade-off a lot of times. So for 1D, there's no trade-off because you can just refine it to hell and you can get a solution. But for 2D and 3D, it becomes an ordeal.
So like when you have like over excessive amount of.
Yeah. Yep, exactly. Yep. All right, any other questions before we wrap it up? Okay, and so that's all we got time for this week. So thank you everyone for tuning in. Hopefully you guys enjoy our first Matlab activity, and hopefully that'll get you going for the homework. So the homework, it is a bit of a doozy, and right now you won't be able to do everything on the homework, but you should be able to do the first half. Because the second half of the homework is what we're going to cover next week, which is 2D diffusion. Okay. And so next week we're going to start to do some really cool stuff in MATLAB, but it is a little bit heavy. All right, so thank you everyone for tuning in today. Hope you guys enjoy the rest of your evening, and I'll see you next week. Yep. Oh yeah.
I haven't checked it, but yeah, maybe 35 minutes. Just went up. What do you want?
I'm still trying to install a power,
Uh,
and that's if I don't get freeway for the first like half of the drive. Yeah, I think where did I drive, guys? I'll pay you for asking.
Because it was fine.
It's this late already. Like,
Go home.
Yeah,
But they all have.
I mean, that is everyone going home already. So
It sucks too, because like, the first 2 weeks I was watching, I was checking like, basically sick. And now obviously you got again, and I'm like, what could possibly be causing this?
So you have to indicate a pause vector.
What are you gonna do, right? Yeah.
I just saw you yesterday, so I'm so upset. You.
You guys have to show one?
yeah, we got to present now.
Are you guys ready for that?
More or less. I mean, it's not that bad. It's just timing them up. It's like, hey,
It's nothing.
yeah, but there's this cool thing we're playing on. Stay tuned. That's about it.
How come you guys have to get the reports?
Not often this time.
Okay.
Last semester was every week practically. Yeah.
I have another class.
Really doesn't ask us anything.
Either try and then I'll try.
He's like, you guys got it, right? And I'm like, oh, we know we have questions. He's like, no, you guys got it. Thanks.
Ready?
There you go.
Hell yeah.